All right, this is Chapter 8 for Physics 151, beginning with the questions. First question number 6. Question number 6. How can the distance to an object be measured by bouncing a wave off of it? This is similar to what bats do. You measure the amount of time that the sound wave requires. So here you would have a speaker, and it would emit a wave with a certain velocity. And here's your object over here. So that wave will travel, and then it would be reflected off. And by measuring the time required to go from the object and back, then you can find the distance, because I know that my distance is what velocity times time. And if you measure the time, and I said bats do this, we do this with ultrasounds, we do it with other measuring devices using sound, we can determine that distance and even figure out by scanning your device across a particular object, you can pick out features in the object as well by measuring those particular distances. So measuring, for example, the distance from here to here, and then measuring the distance from there to there, and mapping out the features on the object. Question number 9. What is the primary difference between ultrasound used for diagnostic purposes and that uses for therapeutic purposes, and what are known hazards of each? Well, the difference between diagnostic, like ultrasound scanners that they use for, say, babies, for example, and therapeutic. The main difference in these is in the intensity of the wave. So the intensity of the sound waves used for diagnostic purposes is very much smaller, an order of magnitude or more smaller than that used for therapeutic purposes. Because for therapeutic purposes, these sound waves are actually used to warm the tissues, the muscles. And obviously if you have too high of an intensity, then you run the danger of actually damaging the tissues, burning them. So that's one danger. That danger is not really present for diagnostic purposes just because the intensity is so low that there's little or no danger of actually harming the tissue. So that's question 9. Question 15. Loudspeaker boxes are designed so that they do not resonate at normal audible frequencies. What would the effect be on music produced in a loudspeaker box that resonated very well at 300 hertz, which is a frequency that you can hear? Well, remember we heard the 300 hertz tone as sort of a mid-level hoo hoo. That's about a 300 hertz tone. And if your loudspeaker box resonated at 300 hertz, then you would hear your music coming out of the loudspeaker, and then you would also hear that ooh, that 300 hertz tone. So in words, the reason you build your loudspeaker box to resonate at a much lower frequency is so that you don't hear it. So the effect would be that you would hear the resonant tone or the resonant frequency in addition to the music. And you don't want that. The resonant frequency exists, except it's just so low that you can't hear it. All right, question 15. Question 21. A sonic boom can break windows. What is the mechanism by which the sound does its damage? In short, this is constructive interference. This occurs when the object that's producing the sound travels faster than the sound wave. So in this case, the plane, which is the object producing the sound, travels faster than the sound wave. And basically those waves are able to catch up with one another, and you get a wake. This is like if you have a duck that's going through the water. This is my duck. You get the idea. he's traveling in this direction, and we get this wake of waves that can catch up with one another. So let's see, let me show you a picture. Here it is. So you see how the duck is traveling in the water, and he's generating these waves, but he's actually traveling faster than the waves are traveling, and it creates this bow shock where the waves are beginning to catch up with one another. You see that in lakes as well with boats that are going at fast speeds. They're traveling at a speed that's faster than the waves that they're generating, and that creates a wake, or which is similar to a sonic boom. Okay, I think that's it for the questions. Let's move on to the problems. Problem number 1. What is the time required for one complete vibration that operates at a frequency of 2 megahertz? So my frequency is 2 megahertz. That's 2 times 10 to the 6 hertz. And I just want to know the time for one complete vibration. Remember, a hertz is equal to 1 inverse second. And so my period is just 1 over the frequency. And I can see that from the units. So that's just 1 over 2 times 10 to the 6 hertz. And I get 5 times 10 to the minus 7 seconds. So that's the period, the time for one complete oscillation. Problem 2. What is the frequency of a sound wave made by a tuning fork that requires 2.44 times 10 to the minus 4 seconds for one complete vibration? So here I'm given the period, 2.44 10 to the minus 4 seconds. And they're asking for the frequency. So similar to what we had before, it's just 1 over the period. So 1 over that value will give me the frequency, and I get 4100 hertz. Or actually, yeah, 4100 hertz. Now problem 7. So you need to be able to go back and forth between period and frequency and know how they're related. Frequency is 1 over period. Problem number 7. Calculate the wavelengths of the lowest and highest frequency sounds normally audible to humans. That is frequencies of 20 hertz and frequencies of 20,000 hertz. Given the speed of sound, velocity is 344 meters per second. So now you also need to know what is the relationship between velocity, frequency, and wavelength. And looking at the units can really help on this, although you'll have an equation sheet. But the velocity, which is meters per second, is equal to the wavelength, which is in meters, times the frequency, which is 1 over seconds. So you see the units check out. So my velocity is wavelength times frequency, and here I want to know wavelength, so that's velocity over frequency. That's 344 over 20. And that gives me a wavelength of 172 meters, or excuse me, 17 meters. That's for the lowest sound that you can hear. And then the wavelength for the highest sound is 344. That's the speed of sound, meters per second, over 20,000. That's in hertz, or 1 over seconds. And that gives me .017 meters. All right, or 17 millimeters. So those are our answers. So you also need to know this relationship, how velocity, wavelength, and frequency are related. Now, of course, you'll have both of these equations on the equation sheet, but it's useful just to know that relationship so that you can pull it up readily. All right, problem number 10. At fireworks display, a person noticed that the sound of an exploding shell arrived 0.3 seconds, so T is 0.3 seconds after the flash from the explosion. How far away was the person from the explosion at the speed of sound is 340 meters per second? All right. And can the time needed for the light to arrive be neglected? And it gives the speed of light as 3 times 10 to the 8th. So this is c. This is the speed of light. We'll get to this later. Is 3 times 10 to the 8th. All right, so first of all, we just want to know the distance. And so the distance is velocity times time. That's a basic kinematics. So 340 meters per second. And it required 0.3 seconds. So 340 times 0.3 is 100 meters. So it's about 100 meters away. And now we want to know, well, is the time for the light to travel to you, can that be neglected? You see it first, and then you hear it, right? And so we want to know how much time does it require for the light to get there. So we say T is D over V. We now know the distance. It's 100 meters over the speed of light, 3 times 10 to the 8th meters per second. And I get 3 times 10 to the minus 7 seconds. So it's less than a microsecond, a third of a microsecond. And so the time for the speed of the time for the light to travel is negligible compared to the time for the sound, which is 0.3 seconds. All right, problem 10, problem 15. What is the sound level of a sound with an intensity of 10 to the minus 7? So I is 10 to the minus 7 watts per square meter. And I want to convert that into decibels. The number of decibels is 10 log of I over I naught, where I naught is the threshold intensity that the human ear can hear. So that's 10 log I naught is 10 to the minus 12 watts per square meter. And I here is 10 to the minus 7. And we want to know what are the decibels of that, watts per square meter. All right, so let's say this is equal to 10 log of 10 to the 5th. 10 to the minus 7 over 10 to the minus 12 is 10 to the 5th. And remember, when I take the log of a number, it's just going to be the exponent of that 10. So this is going to be 10 times 5, which is equal to 50 decibels. So that's my answer. So you need to know sort of how logarithms work. If you want to do them in your calculator, I'm okay with that, but they're going to be simple logarithms like this. So you should just be able to look at them and say, well, the exponent of this number is the answer. And then, of course, you multiply it times 10. All right. Well, when I go the other way, too, was problem number 17. What is the intensity in watts per square meter of a 40 decibel sound? So here we have beta equals 40 dB, and my I naught, remember that's my threshold, 10 to the minus 12 watts per square meter, and I want to know what is I. So I start with the same expression, 10 log I over I naught. So that's 40 plus 10 log of I over 10 to the minus 12. I divide both sides by 10. Gets rid of that 10, so I get 4 equals log of I over 10 to the minus 12. All right, so I know that this has to equal 10 to the 4th because the log of that number is 4. So it has to equal 10 to the 4th. So I can say 10 to the 4th equals I over 10 to the minus 12. I multiply those two, multiply 10 to the 4th times 10 to the minus 12, I get I as 10 to the minus 8 watts per square meter. Problem number 17. If you have this on your test, it'll be something very similar to this. Give you beta or give you the intensity and ask you to find the other, either the intensity or the number of decibels. Let's see, number 31. Problem number 31. Many cars have 2 horns. Suppose a car has horns that emit frequencies of 150 and 150.4. So my frequency 1 is 150 hertz. And my frequency 2 is 150.4. And I want to know what is the beat frequency, and then what is the time between beats. All right, so my beat frequency is just the difference in these beats, F2 minus F1. Remember in class I showed, or we played a 300 hertz and a 305 hertz, and the frequency of the beats, that wah 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 wah, was 5 hertz. So it's just the difference, 150.4 minus 150. And that's, of course, equal to 0.4 hertz. And then I want to know the time between the beats. This goes back to our period and frequency relationships. It's 1 over 0.4. What's that? 2.5. 2.5 seconds. So there your difference is pretty small in your frequency, and so your beats are going to be much more widely spaced. So it's going to be like wah, 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 like that. 2.5 seconds between them. All right, 33. Beats are kind of cool, I think. A low-flying jet actually approaches a stationary observer on the ground at a speed of 1,000 kilometers per hour on a day when the speed of sound is 345 meters per second. If the engine emits a sound frequency 4,000 hertz, what frequency does the stationary observer receive as the plane approaches and as it flies away? So this is the Doppler effect, and we detect this, like, for example, if a car is coming towards us at a certain speed and they honk their horn, it has a certain frequency. But as it's coming towards you, that frequency sounds higher than it actually is, and then as it's going away from you, it sounds lower than it actually is. That's because you're giving the wave an additional speed, right? So you have this car, and it's traveling in this direction. It's emitting these sound waves, all right, which travel at a certain speed, but then the car has a certain speed too, and so it's basically giving that wave additional speed, which increases its frequency. And then as it's going away from you, it's like it's stretching out those waves. So we can calculate that shift in the frequency. This is on your equation sheet, but the observed frequency is equal to the ratio of the velocity of the wave over the velocity of the wave minus the velocity of the source. And this is times the frequency of the source. All right, so let's see, we had the velocities were given here. Problem number 33. The velocity of the wave is 345 meters per second. There are some examples in your book as well on this. And then the velocity of the source, this was a jet, was 1,000 kilometers per hour. So I can convert this to meters per second. 1 hour is 3,600 seconds. And 1 kilometer is 1,000 meters. However you wish to do that, but so that's 1,000 times 1,000 over 3,600. I get 280 meters per second. All right, so now my observed frequency for coming towards me is going to be the velocity of the wave, that's 345, over 345 minus 280, times the frequency of the source, which was given in the problem, 4,000 hertz. Now let's see what I get here. So I get 345. Oh goodness, that's a lot higher. So I get 21,000 hertz. 21,000 hertz. It seems really big. Let me just check that answer. Yeah, that's right. 21,000 hertz. All right. And then when the jet is going away from you, the only difference that we're going to have is that this number, because it's going away from you, the velocity of the source we're going to have as a negative value because it's going away from you. So that would make this become a positive sign. And then our observed frequency would be 345 over over 625 times 4,000. which is 2200 hertz. So it's a lower frequency. So I believe that's the end for chapter 8.